name is George Allen. I'm the oldest employee of nTop by a very wide margin, so I've been around for quite a while. And you know, I do what old guys do. I provide perspective, breadth of vision. I get to say, you know, we tried that in the 70s and it didn't work. And specifically today, I'm going to talk about how we got where we are in terms of geometric modeling. You know, we at nTop have invented some new approaches. So why? What's wrong with the old approach? Why was the old approach successful? Why wasn't it? That kind of thing. I noticed that my timer isn't started here. Does that mean I get to speak forever? Okay. Oh, okay. Okay, so I'm a mathematician. I worked on NX and related things for 4 decades, did all kinds of stuff, but my real area of expertise is geometry, solid modeling, NURBS, what have you. As Brad said, I've been a nTop fellow since 2019. It's a great job. I get to do more or less whatever I want. And I'm based in Okinawa, which, depending on who you talk to, may or may not be a part of Japan. Clicking, apparently. Oh, there we go. Okay, so here's the topics for today. I keep expecting this to be back here for some reason. So we're going to talk about boundary representations, good, bad, alternatives, and so on. So just to make sure we all know what a boundary representation is, it's simple. It's a collection of faces forming the outside skin, the boundary of an object, and these faces are sewn together by so-called topology items, so we're all on the same page. Okay, so back to where things started, 1970s, commercial CAD systems, 3D systems started to appear. Systems most of you have probably not heard of because they're all dead except for Unigraphics NX, so computer vision, CAD, and Applicon. These systems were kind of boundary representation systems, but they were rudimentary in the sense that the faces had to be four-sided. In other words, they weren't trimmed. And you could, if you were clever enough, you could sort of glue these four-sided bits and pieces together, and you could actually make a solid model, or at least in your mind it was a solid model. Here's some examples. The interesting thing about them is, you know, you got to make green lines on a black background. They were all the same, unless you were willing to pay IBM 300K, in which case you could get white lines on a black background. Then, fairly soon after that, a generation of systems that we called CSG systems arose, and in some sense, these were the first commercial solid modeling systems. So you got to do a lot of the same things that we get to do today. You know, you got to make primitives and combine them with Boolean operations. And the operations were saved in this tree structure, which is sort of similar to what we do today. The interesting thing about these is that most of their applications were based on the contents of that tree. So we had to produce sort of very simple boundary representations, or at least lists of edges, because we had to draw those green lines, right? So you got to figure out where those green lines are. But we only did it sort of begrudgingly. We didn't really like producing boundary representations because it was pain, it's still a pain. So most of the applications were based on the tree. Here's some systems from that genre. I'm sure you've never heard of any of them, including Unisolids, which is the one I developed, but didn't go very far. Too bad. Then people started to say, well, you know, wait a minute. Do we really have to start over with this CSG idea? Can't we just take this surfacing stuff that we've already got and sort of turn it into solid modeling systems? And you can. So first of all, you have to get rid of the four-sided limitation, so you have an ability to trim surfaces, and then you invent some topology structures to glue all these things together into solid objects. So systems like this began to appear in the early 80s. But you know, the solid models we built were really just collections of surfaces like we had before. So the really nice thing was you could reuse all your old applications. Any application that worked on a surface 5 years ago will work on the faces of a solid modeling today because they're essentially the same thing. Some examples: Medusa, Euclid, both dead. Then in the late 80s, along came parametric technologies. And they had this clever idea of instead of, after people had done Boolean operations and other operations, instead of sort of throwing those away, let's save them in a tree like the old CSG systems did. And then we can let people fiddle with that tree and they can replay the tree, and it'll produce a new boundary representation and we'll get fabulous editing capabilities. And they were fabulous. But the interesting thing here is that this really didn't affect the applications at all. The applications were still based on the boundary representations. The new tree thing was really just a user interface device. So again, there's continuity with the past. We get to, you get to reuse all the same boundary representation or surface-based applications that you used to have. You don't have to change them at all. The only thing you do is tack on the tree as a user interface device. So really, the reason that boundary representations became dominant is continuity. We get to reuse the old applications over and over again. We had old surface-based applications, and we could reuse them in boundary representation systems, and adding parametrics didn't change the applications at all. We still had all these applications based on boundary representations. And the CSG systems didn't have this sort of continuity, so they died. And not much really changed over the course of the 50 years from a geometry point of view. We added a few new surface types, but the data structures in boundary representation systems today are more or less the same as they were 50 years ago. So continuity is the thing. Nothing changed in the applications, nothing changed in the data structures. All right, so that's how we got where we are. Is that good or bad? Well, there's various pros and cons of boundary representations. I don't have time to talk about all of them, but I'll talk about some of the more interesting ones. The first thing is BREP systems were fabulously successful. You can look around you and pretty much everything you see will have been designed in a BREP CAD system. And CAD vendors make huge amounts of money selling this stuff. And I've personally made quite a bit of money selling this stuff, so good. One of the interesting questions is, are they watertight? Well, of course they are. People design boats with them, so they must be watertight. The real answer is that the topology provides a sort of a caulk that seals the cracks, and the people that claim the models aren't watertight are people who don't know how to use the caulk properly. Do the boundary representations have properly describe the interior of a part? Well, no, they don't, but it doesn't really matter, because you could add on some sort of field that described the interior, and that would solve that problem. So it's a shortcoming, but it's an easily fixable one, so who cares? The big one, I think the biggest, is that BREP systems are fundamentally fragile, and they're fragile for a couple of reasons. One is BREPs have these edges all over the place, right? And to compute these edges, you have to intersect surfaces. And intersecting surfaces is hard. Intersecting surfaces that are coincident or tangent is pretty much impossible. It's what mathematicians call an ill-conditioned problem, which is a fancy way of saying there's no way in hell you're ever going to solve it reliably. So there's that problem. The other one is that in some kinds of modeling operations, the topology gets really, really complicated. So when fillets start overlapping, or when you start making thick-walled shells, if you've ever used a CAD system, you know that those things go wrong. And it's because the topology is so complicated that even the clever guys in Cambridge can't figure out how to do it. So they're fundamentally unreliable. If you're a human being, a clever human being, you know the workarounds. You tweak things a little bit and they start to work, right? You can do that, but a program can't do that. So when we start doing computational design, this is a problem. The other thing is that you've got to get it all right. It's not good enough to correctly calculate 99 or even 99.9% of the edges. You've got to get them all, because the data structure demands that all the edges are there, even the ones that you don't care about. So we're doing all this ridiculously difficult computation to make the data structures happy, not to make you happy. It's stupid. Next problem is verbosity, so poor scalability. it might seem counterintuitive, but a lot of the data in a boundary representation is actually in the edges, not in the surfaces. So a boundary representation is something that's got a pile of edges in it, so it's going to take a pile of space. I don't think that's fixable. The other one is that today's boundary representations are missing some surface types that are very useful, like gyroids and what have you. And so those all get approximated by NURBS, and that takes space too. I think that is fixable. There's no reason why BREP systems can't include implicit surfaces, gyroids. Another big one, BREP systems were designed for computers of the 1980s. You know, this isn't the 1980s. Computers today are just different, with multiprocessing, GPUs. And BREP algorithms are just not well suited to this kind of computer architecture, so we're wasting computers. Are there better alternatives? Well, of course. Well, first of all, why do we need alternatives? You know, BREP systems have been doing well. What changed? Why do we need something new? And I think the answer is the things listed down the left-hand side there are placing new demands on BREP systems, and they're not able to deliver. So, or another way of saying it is that BREP systems have always had these sort of shortcomings, but because of changes in the world of engineering and the world of computing, those shortcomings are becoming much more significant. They're becoming roadblocks. They're not just inconveniences anymore, they're roadblocks. So we've got to do something. So computational design, we want to build a model and we want to iterate like crazy, right? To run around the design space, find optimal designs. And you can't iterate effectively if each iteration risks failure. So you really need reliability in order to be able to iterate, to do computational design, to produce better products. So it's this inconvenience of BREP failures is now a roadblock. So what are we going to do? Well, you know, here's one idea. I don't claim it's the only one, but it's the one we're using at nTop, and I think it's promising. So we have this implicit tree, and we try to use that for all of our applications. Sure, we produce meshes and BREPs, but we don't really want to. It would be nice if we didn't have to. And we try not to use them. We try not to be dependent on them. We have to produce them for export and data interoperability reasons, but we try not to rely on them. We all know what implicit modeling is, I think. You make up some function that's negative inside, positive outside, and that's what we use. I don't want to go into the details of it, but the point is it's fundamentally different from BREPs. The BREPs on the left require intersections and curves and what have you. Over on the right, we've just got these functions. We do mins and maxes. It can't possibly go wrong. Taking the minimum or maximum of two functions cannot possibly fail. So we get the reliability we want. Complex geometry is not a problem. You've seen examples that are much better than mine, so we're good at that. We're leveraging modern computers. We can do things fabulously fast. It's really quite amazing. Are there new problems? You know, there's no free lunch. We've invented this new approach to modeling, but it solves a lot of the problems with BREPs. And the question is, does it create any new ones? Well, yes, of course it does. And the big one is we've made an island for ourselves. This implicit modeling world is a beautiful little island, but we've got to connect it to the mainland of BREPs and traditional CAD and what have you. And making that connection is one of the biggest problems that we face. Some companies are quite happy to just design something in nTop, print it, done. But in a lot of other companies, no, that's not good enough. If my geometry isn't in a CATIA file or an NX file, it may as well not exist, not interested. So this problem has to be solved. And there's a couple of ways to do it. If you've got that island problem, I'm an expert, I live on a little island, so there's two ways to do it. The first way is to build bridges, and of course that's what we do. We have functions that export, that take implicit geometry, convert it to BREPs or meshes and export it. And when I joined the company, we were really bad at this 4 years ago. And we've been getting better gradually, but I think we're still not done. So the new Sequoia kernel is a big help. So you'll be seeing some improvements in the next 6 months or so. So we continue to work on this. We've got one of our smartest guys who may or may not be in the room working on this, and we're making good progress. The other thing you can do is try to make your island bigger, get more people to come and live on your island, and we're working hard on that too. You heard from the people in the panel discussion. So nTop Core is a thing we're providing to people so that they can come live on the implicit modeling island, and that's working pretty well. It's not that hard to write applications based on implicit models, and we're making good progress on doing that. So in summary, BREPs have served us well, and they're still good for a lot of things. But the world has changed, and BREPs haven't. And we're going to have to do something to accommodate the changes in the world. There's a bunch of new problems that BREPs are really not very good for. Implicit modeling solves those problems, but it creates the connectivity one. And we've got two ways to solve that: the better bridges approach or the bigger island approach. So we've replaced one set of problems with a new set, if you like. I think the new set of problems is easier to solve. We've been working on the old ones for 4 decades, and we still really haven't licked them. I mean, BREP systems are still unreliable and verbose and inefficient. So, you know, it's time to take a whack at the newer problems, I think. So I think the newer problems are easier to solve than the old ones are. I think they're a better, offer a better opportunity for a future, and that's why I now work for nTop and not for Siemens. So. Okay, thanks. That's everything. Arigato.